Thanks, Jenny. Today I'm going to talk a little bit about turfgrass management and how we can use turfgrass to mitigate climate change. So the first thing that we really need to do is come up with a definition of turf as a whole. And so we can define turf as a community of grass plants that form continuous cover, and they're under frequent mowing and traffic. So the two big terms up there that make maybe turfgrass different than a lot of crops is one, that it's under continuous mowing. A lot of crops don't get mowed, but we do, as well as traffic. So that makes it a little bit different too than like a normal grassland that we might think of on a prairie or some other place that may not be managed the same way. There was a study that was done in 2005 and published. It was done by Millisy, and this group of scientists went in and basically used satellite imagery to determine how much area of the United States was covered in turfgrass. And so the map looks pretty sparse. It doesn't look like there's a ton of turfgrass, but whenever they did all the numbers, they ended up figuring out that there was about 164,000 square kilometers of turfgrass throughout the United States. That would be equivalent to about 40.4 million acres, and that would make it the largest irrigated crop in the United States. That's 3 times larger than what we would see for a corn crop throughout the United States. So it's a very expansive amount of land area, and I'm sure some of you are thinking, and some of you may have poor thoughts about turfgrass. It uses too much water. It doesn't do a lot of good things for our environment, so why are we having so much turfgrass in the United States as a whole? But good news for me, I guess, and hopefully I can help you understand some of these things. That does provide some environmental benefits as well. So carbon sequestration, reducing urban heat, those are the two main things that we're going to talk about. But you can see there's a whole list of things up here that are positive things that turf provides to our environment. And we're going to focus on these first couple. So when it comes to carbon sequestration, turf can be very beneficial, first of all, because we don't cultivate it. It's a perennial crop that basically is just there. So it's always taking in CO2 from the atmosphere, and it's depositing it in the soil as soil organic matter. And it's just a great way to sequester carbon from the atmosphere into the soil with limited disruptions. We also have some negatives about turf, of course, especially situations like a golf course. We manage those pretty intensively. They use a lot of fossil fuels as we're mowing the grass very frequently. We're irrigating it fairly often, and we're fertilizing it. But there was a study that was done in Ohio in 2011, and they went to like 10 to 12 different golf courses within the Chicago or area, I believe in this particular case, Central Ohio, sorry. And they went and they sampled golf course fairways at a number of different locations. So a golf course fairway, just to give you a little bit of size perspective, is about 8 to 12 hectares, or 20 to 30 acres is a very normal size for a golf course fairway. They're not managed as intensively as something like a putting green, so we're not out there mowing it daily, but probably about 2 to 3 times a week we're mowing it. We're irrigating it fairly frequently, probably about the same amount 3 days a week, probably. Fertilization, fungicides are applied in this region specifically, and those are some of the big ways that emissions occur as we're managing the turfgrass. But they basically went around and collected samples, and they broke them into 4 different areas or depths. Okay, so we have 0 to 2.5 centimeters, 2.5 to 5 centimeters, 5 to 10, and then 10 to 15. And so based on the results that you can see, this data table is from their research. The top 1 inch, or 2.5 centimeters, gets a very astronomically high sequestration of carbon very quickly. And so it reaches its equilibrium point within about 15 to 16 years, and after that it pretty much flattens out. And as we move down deeper into the soil, the equilibrium period shifts to a lot longer period of time, but the depth or the amount of carbon sequestration that's taking place also is reduced. So ultimately, based on this research, they were able to determine, because in addition to looking at the sequestration potential, they also looked at the emissions. And the main emissions that occurred on this particular area were from diesel and gas usage. The combustion of the engines, all those things were the primary emission that the golf course had. But they also had really high emissions from fertility applications, fungicide applications, and irrigation. So with that being the case, they took everything together and created a budget, and they basically determined that the golf course was a net sink for carbon for about the first 30 years, whenever that high elevation of carbon was being taken into the soil. But after that point, once it reached that equilibrium perspective, then it basically became a slight source in that case, because we were giving off more carbon than it was taking in. So we wanted to see what the golf courses here in Lubbock may be like. So I have a grad student who's just kind of completing up some laboratory exercises. We went to 5 different golf courses here in Lubbock. They have bermudagrass on other golf courses. We sampled 6 different fairways at every golf course, 3 locations within a fairway, and then we only did 2 depths. We did 0 to 7.5 centimeters, and then we did 7.5 to 15 centimeters. But we kind of underwent the same kind of processes that previous research did. And you can see the data didn't exactly follow along with my hypothesis that I thought we might see. Bermuda grass is a very aggressive grass. So anybody who has Bermuda grass in your lawn, you know that you can't kill it. It likes to grow into your flower beds and all the places that you don't want it to go, because it has rhizomes and has stolons, these little stems that help it move across the ground and make it very aggressive. Well, with that, I thought we would produce more organic matter that would then in turn result in higher sequestration levels. But ultimately, you can see from the data that our values are actually a little bit lower. A couple of things could be going on there. First of all, we're combining a lot more soil depth together than what they did in that previous study. So we're taking the first 2 numbers that they had and combining them with even some of the lower depths that they had in the Ohio study. So that could be one reason that our numbers are a little bit different, but they're definitely not higher than what we would have seen in Ohio compared to here in Lubbock. And it could be too that with Bermuda grass, it does have a pretty short growing season. It is very aggressive, but here in Lubbock, it's not getting a full extended growing season that you may see in Florida or San Antonio or somewhere where it's warmer throughout the year. That may really help increase the sequestration potential. But here in Lubbock, it was more moderate. And so we definitely have a little bit more work to do to try to finalize everything and figure out all the intricate details of the research. But that's one thing that we could think about or look at from a climate science kind of perspective. The other big thing that our turf grasses can provide is environmental cooling. And it's done so through transpiration, of course, which as the plant is photosynthesizing and water is available for the plant, it's taking up the water and it's releasing it to the atmosphere, and that causes evaporative cooling. Similar to if you were to sweat during a hot summer day and the sweat evaporates from you and it cools your body. It's the same principle with different plants. And the key principle is kind of the last bullet, is that the plant has to have available water to be transpiring. And if it's not transpiring, then it's not going to be doing our environment any good from a urban heating standpoint. It's not going to be cooling the atmosphere very much. So here's a question that we could ask, is how much supplemental irrigation do turf grasses need in Lubbock, Texas to provide this environmental cooling that we expect or want it to have? So we know it has to have water, but what's that optimum amount of water where we get the best of both worlds, basically? So we've actually just began the process. This past summer, we installed a drip system at our Quaker Research Farm that's here in town. The drip system is set up with 5 different irrigation zones, and they're spaced out they're randomized over space. So we have long strips, and we have 2 different replications of each irrigation zone that are spread out over space and randomized. So from a statistical point of view, we have a good ability to randomize our plots and look at various grass species with different irrigation levels. So, maybe a proposed irrigation level that we would look at might be 100% ET, return 80, 60, 40, and 20. And we can get a linear kind of graph to see where the optimum amount of water for each turfgrass species would be. So that's something that we'll be beginning very soon. So here are some of the different grasses that we're going to plant. We have a couple of different Bermuda grasses, buffalo grass, habiturf is a native grass mixture of seeds, and then a couple of zoysia grasses that are also warm season grasses. And then the last three are cool season grasses, because everybody knows that tall fescue takes way too much water, right? So we're going to see exactly how different those different species are in our particular climate with this particular research. So just a few things. We do a lot of visual work, of course, in turf because we're an aesthetic type of crop. So we want to make sure it looks good. But in addition to that, we'll take digital image analysis, volumetric water content of the soil at these different irrigation levels, and things like canopy temperatures to understand more about the transpiration rates and how that could impact the ambient air around the turf grass itself. Just a little bit quicker image on the digital image analysis. We use some software that basically picks up green cover. So as the plants are starting to go into dormancy from drought stress, we could kind of quantify how much drought stress is present with different grasses at different times of the year. And we would use a similar process to what's on the screen in doing that to come up with percent green cover for different turf grasses. And then here's just a look at the plots themselves. This was this last summer. We started some of the sod establishment. We still have some grasses to establish. But we would like to make this an outside kind of laboratory for people to come and look at the different grasses, as well as a research project where we can kind of identify some of those key principles that I had mentioned previously. So with that, if you guys have any questions, I'd be happy to entertain them and try to answer them. Yes?
Just a comment, you pointed out the fact that it was relatively dry, and those of you who've been around here for the last few years probably recall that we had the driest period in 100-year record. So on the other hand, from precipitation and temperature, climatologists usually look at maybe a 30-year average. So
okay.
You probably don't want to plan a 30-year program right now. Certainly longer than
sure.
that dry period you endured.
Yeah, sure. And I mean, all the golf courses were irrigating, so it wasn't like the grass was under
right.
drought stress per se. But I just thought that might be a reason for a lower number compared to we were in optimum conditions. So.
For carbon sequestration, do you know how buffalo grass compares to Bermuda?
I do not. And all the studies I've seen have really been from Colorado State and then that study in Ohio. And so that's one reason that I wanted to do this on Bermuda grass, because I hadn't seen any studies, particularly on a warm season grass at all. So I definitely don't know buffalo grass to Bermuda grass. But that's a good question. Yes?
For the average homeowner, what have you looked at amount of carbon in just yards around Lubbock at all, Joe?
I have not. No. I mean, that also could potentially be a really relevant study in the future.
Well, the only reason I mentioned, so from my incredibly college one year, we went out and did that. We went out and looked at how much carbon was in older neighborhoods and whatnot. I mean, interestingly enough, I got to some homes where I could get soil carbon in Lubbock up to about 8%.
Really? Wow. Yeah.
Under Bermuda, but.
And I think some of our numbers might have been there, but it's just whenever you look at the total and then look at the, just kind of the values, there's a lot of variation.
Right.
And there are some things that we're talking about doing in some urban environment. So that might be an easy thing for us to just collect some soil from different yards and just evaluate based on some of those same principles.
In terms of the urban heat island mitigation, I think a lot of city sustainability departments are looking into ways where they can actually maybe reverse the concrete and asphalt they put in and try and replace it with natural surfaces again, such as turf. Have you looked into how difficult of a process that would be? Because I feel like it is a pretty difficult process, but if you can really show the value of decreasing urban temperatures, that would be really interesting.
Yeah, that's a good point. I know, so like converting from concrete to another.
They really want to actually go in reverse.
Yeah, I don't. I could see that being a challenge, and maybe it just depends on the construction and different things that were done. I don't think getting rid of concrete is probably the most expensive part of the deal. But one thing, and I didn't necessarily talk about this, but soil plays a major role in the water use efficiency of any of these different turf grasses. And you can look at different urban areas where they've mandated that there's at least 4 inches of topsoil, for instance. And there were studies that were done at Texas A&M previously that grasses grown on 4 inches of topsoil under 60 days of drought stress with no water, they all died and they never grew back. But under a full substantial root zone where the grass can kind of search for water deeper in the soil or have more access to water, all of those grasses survive 60 days of drought. And once you start rewatering them, then they grow back. So the soil depth and the soil characteristics are going to play a huge role in water use efficiency, which is going to in turn play a role in heat island mitigation and all the other things that we're talking about. Okay, thank you all for letting me come and talk.